Hello, everyone. Lucas here. Okay, I think now you're
Hello. Yeah.
unmuted, Rajneesh.
Sorry about that. Yeah.
Uh,
Hello.
so yeah,
Hello. You can hear me now, right?
hello everyone. My name is Lucas. I'm a software engineer here at Microsoft. I actually worked last year as a solution engineer for the Cosmos DB for Postgres team. So one of my main jobs was to help customers adopt Cosmos DB for Postgres and Citus, of course, and how they can migrate for their workloads to this tool. So we're going to present for you today how to design multi-tenant SaaS apps with Azure Cosmos DB for Postgres. So you can introduce yourself now, Rajneesh.
Yeah. Thanks, Lucas. So I'm Rajneesh, and I'm the cloud solution architect as well as technical insider for Azure Cosmos DB for PostgreSQL. And today, as Lucas said, we'll be walking you through the session, talking about Azure Cosmos DB for PostgreSQL, how it can be leveraged for SaaS application, or so to say, tenant-based applications. So with that said, we can just quickly move on to the slides and the start of the session.
Yeah,
Uh,
before
uh,
that, yeah, say hi to your moderator. So Goran will be your moderator for the session. So any questions you have, anything you'd like to ask, please send on the chat and he will forward those questions for us.
yes. Yeah. So just before we start, I mean, the topics which we are going to cover, which we are going to be covering in this live session, those are available on the link over here as well. So once you attend the session and you want to yourself go ahead and do hands-on on this particular session, you can go here, use this link, and get all the contents and all the steps and instructions to kind of execute this particular session on your own. And let's make this session interactive. If possible, you can just on the chat, you can just say hi and put in your questions, and our moderator will try to answer that. Any questions specific to us as presenters here, that may also kind of get directed, and we can try to cover that as well. Uh, Next slide, Lucas. Yeah, so over here in terms of the learning objectives, right? I mean, just to kind of give you a background, over here we are going to be covering how we can leverage Azure Cosmos DB for PostgreSQL for SaaS applications. The scenario here is currently the application is deployed on a single node database, on a single node database, and the underlying database is the PostgreSQL. And the application is scaling. So in order to kind of be with the scaling, the underlying database also needs to scale along with that. So how we are going to scale from single node to multi-node. So if we do that, what all are the steps we need to kind of go through, or what are the architectural changes we need to kind of go through? We're going to cover that. So we're going to be covering something like how do we prepare our tables to move from single node to a distributed node tables, and as well as how do we distribute our tables? What should be the criteria? What should we consider before we start distributing those tables? Once we have distributed and have our tables spread across multiple nodes, how do we monitor the distribution and look into the utilization and ensure that the distribution is working fine over a period of time, because things keep changing, right? I mean, the situation, so the distribution which would have done is based on the current situation scenario, but as and when business kind of advances, the situation changes, so you have to do a continuous monitoring of that as well. So we're going to cover that as part of this session as well.
Okay, so let's move to the introduction.
Yeah, so this Azure Cosmos DB for PostgreSQL is like right now, if you see, it's kind of uniquely positioned for hosting any multi-tenant software as a service application at any scale. And why we say that is because PostgreSQL not only kind of ensures that you are kind of storing the data in a regular database, which is an RDBMS, kind of conforming to different compliance standards which are required, something like ACID compliance, having primary key, foreign key relationship, storing the data in raw format, and while doing that, still scaling and utilizing the scaling capability, which are now being made available in different form of databases like NoSQL and all. In NoSQL and all, where you need to kind of compromise on the relational capabilities of the database. Here, you're not compromising. You are continuing to utilize the features and capabilities of the relational database, being compliant and still scaling using the distribution capability which is built into Azure Cosmos DB for PostgreSQL. This is because we have kind of embedded the CTIS, if you're familiar, CTIS extension into the existing service, which allows us to scale the PostgreSQL database not only just on one node but across multiple nodes.
Yeah, and the great thing about Citus is that it is just a Postgres extension, so you can still have all of the Postgres features, but in a distributed fashion.
Yeah. So let's get into the situation here, the scenario here. So we have a company called Tailspin Toys, who has already implemented PostgreSQL, which is running on single node with some different stores all across the country. But then this particular company is growing. It's adding more stores all across the country. More stores means that more customers, more transactions happening. And what is being observed is that single node is kind of we're filling up the capacity there. So obviously we need to scale out as the business is kind of scaling it out. Myself and Lucas, as a we have been assigned as a data architect to kind of go in and look into like how we kind of scale it out. So what we did was we followed the steps defined. The first step was to really look into the existing data model and identify the tables, what all tables are in there, and then start preparing tables for multi-tenant data architecture, and as well as how we can kind of look into the distribution of those tables in here. So as you can see, it's not very complicated architecture here, but it's running on single node, primarily 4 tables. Orders is the most active table where all the orders are kind of getting stored. There are different reference tables like stores, which contains all the information about stores all across the country, which is kind of which has the primary key as store ID. Then we have the products, all the products which Tailspin Toy is kind of selling. It has a list of all the products built in here. And then the line items, where all line items are being sold as part of the order, is also stored in the line items table. So this is what. So we have to now look into each of those tables and kind of decide as to how do we distribute that. So in the subsequent step, if we move forward, we are going to be slowly getting into that. So now we have to plan out, right? You can, as you know, right, Azure Cosmos DB for PostgreSQL, you can scale from one node to one coordinator node and 20 worker nodes. So 20 worker nodes is the maximum capacity to which you can kind of scale up to. You don't need to it again, you can, it depends on how much nodes you need. We can size that out, and basis that you can accordingly kind of decide on, okay, how many worker nodes you need. Obviously, there's going to be a coordinator node along with that as well.
Yeah, 20 worker nodes is not like the upper limit. Of course, in the UI, you can select up until 20, but if you actually need, you can submit a support request, and it is possible for you to have more than 20 worker nodes. In fact, there are some customers that are running more than 50 workers, for example.
Yeah, thanks, Lucas. Thanks for bringing that up. So, so let's understand the multi-tenant architecture for Azure Cosmos DB for PostgreSQL, right? So it uses a form of like hierarchical database modeling to distribute table data across nodes in the cluster, and we're going to cover in the subsequent slide. If you can move forward. The first and the primary thing is to choose a distribution column. That's very critical. You have to really understand the data and also understand the query which is being submitted by the application and as well as by the end users. And basis that, you're going to choose what should be your distribution column. So in this case, with Tailspin Toys, with this application, the store ID is where we have identified as a column which makes a logical distribution key. And the reason is because most of the transaction orders which are coming in is by store ID. So any of the inserts which are happening are happening for the orders being submitted in a store, or if any query is happening, or any select query is kind of happening on the data, that's happening again with a filter of store ID equal to some value. So when we kind of analyze that, looked into all the query patterns and looked into the data, we decided on using store ID as the column for the logical distribution key.
Yep.
And then the next step is to kind of classify the tables. So as we are bringing in here, we have to classify. So classification is like, okay, which table is, with the existing structure, which table is ready for distribution? When we say ready for distribution, what essentially we check is like, do we have the distribution column present in that table or not? If it is present, typically we say that, okay, this table is ready for distribution. It can be distributed based on store ID. If not, and still we need to kind of go ahead and distribute that table, then we need to do a backfill. Backfill means like you have to kind of populate or kind of create a distribution column in that particular table and backfill or populate that column with the appropriate store ID into it. And that's what we're going to do. In our case, we have one line item table which is identified as backfill, and Lucas is going to demonstrate that to you as to how we are going to be backfilling that. Then we have the reference table. Are there any tables which we can identify? So reference tables are tables which you use for referencing, and those are typically small in size. So if you don't distribute them and just kind of replicate them all across the node, that is also a possibility. Why unnecessarily distribute them? Rather, just a small table, keep all the records into that, and keep it across all the nodes within your cluster. So that's the reference table. We have one of the tables identified as reference table as well in our scenario. And then there are local tables. Local tables are typically stored not at the worker node level, but it is at the coordinator node. And those are typically tables which store user-related information or any user authentication which you're planning to do. Those are the local tables, and Lucas is going to cover that in our subsequent exercise.
Yep.
Okay, so these are some of the steps for the backfill table, right? I mean, as I was mentioning, we have the line item table, which does not contain the store ID, but that line item table needs to be distributed along with the order table. And the whole idea is to have all the tables with the same distribution column co-located on the node. So let's say if you're doing it for store ID 10, for order table, if we have store ID 10, which is stored on, let's say, worker node 1, in the line item table or in the store table, we would also want the store ID 10 records to be co-located on worker node 1 along with the order table. So, so in this line item, we are kind of we are backfilling it, and we are creating a store ID column, and we are kind of populating that in the backfill table.
Yeah.
Lucas, you
When
want
we
to add
say,
anything?
yeah, sure. Yeah. When we say co-located, it means that they are on the same worker node, right? So
Right.
when we distribute by a certain key, for example, store ID, what we're essentially saying is that all stores with a given key will be always on a specific worker, and therefore all the queries that are filtering by that store ID will be redirected to that worker node. So we can parallelize, right, and we can divide data among multiple workers, and therefore making indexes more performant, making background jobs, Postgres jobs, such as vacuuming or something like that, faster as well. So that's what we're talking about here. So co-location is a very important concept in Citus and Cosmos DB for Postgres. So that's what we're trying to achieve here. So let's move forward to the next slide.
Right here. And uh, we also kind of update the table keys here. While we are doing this, while we are having the distribution kind of being done, we can still have the primary key foreign key relationship continue to exist across the table. And that's where we are going to be updating the table keys into that.
Yes,
Lucas,
Citus cannot enforce, since we're distributing data and we're moving data across different worker nodes, there's no way for Postgres to, since we're running on Postgres, right, there's no way to guarantee uniqueness if we don't also add the distribution column to the primary keys.
right.
So that's one step that we need to do in order to migrate from a single node setup to a multi-node setup, right? So we're going to cover this in the demonstration exercise on how to actually do this, and I'll explain you on more details.
Right. Yeah.
And that's now. So
Yeah.
let's actually start doing it. Give me 1 second so I can change to the terminal. Okay. So I have this database here. We don't have any tables on the public schema, so I'm going to create them one by one for you. So first, let's create the stores table. Stores table, as you can see, there's a store ID, a name, and a category. Now we're going to create the products table, which references stores by store ID. And this foreign key will also change because of the changes we'll make to the primary key. So we'll do everything step by step here so you can understand. Next, we have to create orders. Also references the stores. And last, the line items, which does not contain a store ID and thus cannot be distributed right now by the store ID key, okay? So the first thing we need to do here, of course, is to add that store ID column to the line items table, okay? So we just did that, right? The next step here would be to backfill, right, this table with the store ID. As you can see, I haven't added any data to these tables because we have a small issue with the data for this exercise. So unfortunately, we'll have to move forward without actual data, okay? So assuming there was data, the next thing we'd have to do was to create that backfill batch function that Rajneesh showed you on the slides previously. So since we're not doing that, I'm just gonna skip to the index creation step, okay? The first thing we need to do here is create new indexes unique indexes that contain the store ID for each of those tables, okay? So first, orders, right? Next, products. And last, line items, okay? I cannot see right now the chat, so if there are any questions, Rajneesh, can you please interrupt me?
Yeah, sure. Yeah, no questions so far. Yeah.
Okay. So now we have all the 3 new unique indexes created, right? So what we need to do now is to drop the previous primary keys and then create the new primary keys using this new unique index that I just created for each of the tables, okay? So let's do this very slowly, okay? First thing, we're gonna do it for orders. So what I'm doing here is I'm dropping the original primary key constraint with the cascade. And it's important to mention that this cascade will also delete the foreign keys that are referencing this key. So we'll have to recreate those afterwards, right? So as you can see, now we're using the orders TMP index as the primary key. So the name was changed to P key, okay? Table was altered, and we can actually see it here. Oh, it's a bit very big, right? But here you can see that the primary key now contains both the store ID and the order ID. And just to say it again, the reason we need to do this is because there is no way to guarantee uniqueness without having the store ID as the composite, as a part of the composite primary key of the distributed tables, okay? Next thing we'll do, like I said, the foreign keys were deleted. So what I'm doing here is I'm recreating the line items foreign key for store using now the new primary key that contains the store ID as well. Okay, so we did this for orders. So now we have to do the same for products. I'm gonna go faster here because it's pretty much the same concept. Okay. Recreate the foreign key. Line item had had a foreign key to products. So now it has to use the new primary key. And last, we're gonna do the same for line items. Okay. And now we're gonna create, it wasn't deleted, but we'll create now a foreign key to store on the line items table, okay? So now we have the tables prepared to be distributed, okay? It's a very simple thing, right? You just have to drop the primary keys, create them with the distribution key, and then you have to recreate the foreign keys, right? It's a very simple concept. Unfortunately, I'm not able now to show you how the backfilling works. But the idea is very simple. You can create a backfill batch function that will get what's the store ID for each of the line items and then store it on the table itself. And the reason we're doing a batch here is because this table can be huge, right? So it's not a good idea to try to write everything at once.
Right.
With that being said, it was faster than I was expecting, but I think we can move forward now to the next part. Are there any questions so far?
No, I think questions are being answered by the moderator and other viewers as well. So I think we are good there. So no questions directed to us so far.
Yeah. So what we did here, so this is a summary of what happened, right? So the first thing was to provision an Azure Cosmos DB for Postgres database. So I did it through the UI. I connected it using PSQL. I created the tables. I did an ingest using the copy command, right? PG Chrome here, the reason it should be installed here at first, in first place, is because the backfilling job would be executed by the PG Chrome extension, okay? And that function would be executed on the batches. Then we added the distribution key, backfill the missing values. The update application queries here is, I haven't showed any queries for you, but when using Citus, you want to query and filter by the distribution key. Otherwise, all the queries would be sent to all the worker nodes, right? Because there wouldn't be a way to Citus to understand where you should send the query. So you would try to send to every worker, and every worker would then see if it would have the data for that distribution key. So using Citus without actually filtering by the distribution key is not a good idea. That's the lesson here. But yeah, that's pretty much it. And I think we can move forward, Rajnish, to the next step of this lesson.
Yeah, sure. Thanks, Lucas, for demonstrating that. As Lucas said, right? I mean, we have prepared we have identified the tables, and we have prepared the tables to be ready for distribution, right? Like wherever backfilling was required, we backfilled. We identified the column for distribution. We dropped the existing keys, and we recreated the keys with store ID as included as kind of a composite in the composite key in here. So now our tables are ready. Now let's distribute the tables and ensure that there's a minimal application kind of a disruption there, because it's kind of doing the transaction. So if there's a disruption, transactions are not going to happen, and there'll be an impact on the business. So how do we distribute tables with minimal application disruption, right? So if you move to the next slide, the first step is you have to create. So you're moving from single node to multiple worker nodes, right? So you need to create more nodes in there. So you're going to be creating one coordinator node, one node which is in there can be identified as a coordinator node, and then you can kind of create 2 additional worker node. In this case, so we kind of did the sizing and came up like, okay, 2 worker node from 1 to 2 should be good enough for now to kind of support the existing workload which is in there. So 2 ways you can go to the portal and kind of create those worker nodes in here. And now we are into kind of distributing and co-locating the table data, right? So this is how we are going to be distributing and co-locating the table data. So we are kind of in the subsequent step, you'll see the functions which you're going to use to distribute the table, and ensuring that the main table and along with that the other tables are kind of co-located in there. So next slide, Lucas, if you can go to. Yeah, so this is how typically the distribution and co-location of table data would look like. So typically when it gets distributed, it is distributed in a shard. So a shard will have the shard is kind of a logical thing there where you are kind of combining multiple values of the distribution column into one group. For example, we have used store ID as a distribution column, right? So any store ID 1, and along with that in the store table, as well as in the line items table, orders tables, and product tables, as well as other store ID, which is store ID 2, all kind of grouped together. They are forming one particular shard, and these shards can be you can direct or define these shards to be present on any of the worker nodes which you have in your cluster. So we have 2 node clusters. So as you can see, there are 2 shards, and 1 shard on worker node 1, another one on the worker node 2. Now, While you choose to distribute, keep in mind the order of table distribution is important. Because if you don't follow the order, you may land up into error, which is being shown here on the slide. So the order should be that all the reference table, which contains all the foreign keys being referred to or being used in the main table, those need to be distributed first. So we have to, if you distribute the, let's say in our example, if you distribute order table before, let's say, store table, you'll start getting the error, because you won't have a equivalent of a foreign key constraint, primary key foreign key constraint, which is in there. We'll say, okay, hey, reference table store is not in there. So you need to first distribute the reference table. So in our example, store or so to say product, those are the tables which needs to be distributed first and followed by the order table. So that's what the thumb rule is: reference table first, and then the main transaction table. Because you want to add something here?
Yeah, well, I actually just want to pause for a bit and answer the question that was sent on the chat. So the question was, can the distribution key be of any data type, or are there any limitations? It can be of any data type. Yeah. What Citus does in the background is actually use native Postgres hash functions for each of the possible data types that can be in a column, right? The only constraint here is you cannot have natively two columns being part of the same distribution key, okay? In fact, actually, you could write your own hash function, but that's not a good idea, right? So basically answer the question, yeah, it can be of any data type. Okay, so let's move forward. Actually, I lost control of the slides. Now I have control again.
Okay. Right, yeah. So again, now we have identified the distribution, we have identified the order of the distribution. Now we have to look into, okay, while we are distributing the tables, we should have minimal application disruption, which means we should ensure that there is no kind of a downtime or outage of the application, because it's a critical application. Any outage will have a repercussion on the revenue of the company. So there are two ways in which you can do the distribution of the table data. Two functions which are provided within Azure Cosmos DB for PostgreSQL. One is create distributed table, and the second one is the create distributed table concurrently. If you go to the next slide, I think we are covering that, right? We'll move to the next slide.
Yeah, 1 second.
Right, yeah. So when you do a create distributed tables, right, what happens is it's going to lock the table for you and then do the distribution, which means while the distribution is happening, you won't be able to write any transaction or any records on that particular table. So that will stop you from doing that. So you have to be careful, like where you would use this function. You would use this function on a table which is not frequently kind of getting updated. Something like a product table, right? I mean, it's not that frequent that you're creating a new product and you need to, or any existing product is changing for which you need to kind of update. Or example is store. You don't open a store every day, right? Or you don't update the store information every day. So those are the tables which are not very frequently getting updated, and those are small in size as well. So distribution will also not take that much time to do that. So those should be those are the good candidates to go with the create distributed table function, and using that, you're going to be kind of distributing it across the worker nodes. Here again, one thing I want to highlight: there's a co-locate attribute as well, which you need to provide with the function. Where you can say, okay, specify which table it needs to co-locate with, so which is stores over here. The second one, which is the create distributed table concurrently, also allows you to distribute the table. But with that, what happens is it does not lock the table. So you can continue to write on those tables while the table is kind of getting distributed.
Yeah.
But there is a challenge there in terms, because if you allow the write, there is a chance that the table is kind of getting distributed, and there's a chance that you may lose the referential integrity in there. So you have to do it.
Yeah.
You have to have a strategy for that. So the strategy there is to do it in batches, and that's
Yeah.
where Lucas is going to demonstrate how we're going to be kind of doing it in batches
The
in there.
just want to add a few things here, Rajneesh. So if you actually don't specify the collocate with parameter on the create distribution table, it will collocate with every table that has the same data type and value. Okay. So it is also possible to not include the collocate with, but if you want to specify exactly, hey, I want to collocate this table with this one, then you can
Right.
specify using it.
Right. Yeah. Thanks for being there, Lucas. Okay. So okay. Yeah. Okay. So we understand the impact, right, of some tables being distributed while others aren't, right? Uh, Neither of the like. So you have to kind of figure out in terms of like which function you're going to be using on what table to do the distribution, and how you're going to be batching. If there's a huge table, how you're going to be doing it in batches, and then kind of distributing it to ensure that while you're distributing, you're not losing any data integrity in there. Uh, Next slide, Lucas. Yeah, so
Well,
let's
it's
get
my
into the
turn.
exercise. Yeah, yeah. Back to you, Lucas. Yeah.
Okay, so let's go back to the exercise. Give me just 1 second. So yeah, like I said, unfortunately, we don't have actual data here on this cluster. But what I want to just walk you through here, right? So right now we have a bunch of tables in the coordinator, right? So no tables are distributed. And Citus offers a view that can be used for you to see which tables are distributed and which ones are not. Oops. So here, I'm not sure. So Citus underscore tables is a view that shows us which tables are distributed of which type, which one is the distribution column, what is the table size, shard count, table owner, access method, collocation ID. Collocation ID is a column that is used internally by Citus. It's not important for you to understand for which tables are collocated with others. Okay. So we also have a view called Citus shards, uh, which is basically a breakdown of tables and their shards, shard ID, shard name, which node those shards are, the port of the node, and the shard size as well. Okay. Uh, the first thing I want to do to you here is I just want to show you the error that would happen if we would try to distribute the table right now. Okay. Relation stores is referenced by a foreign key from products. Okay. So we cannot distribute this table without also distributing products. Okay. So let's try to distribute products. Is also referenced by line items. Let's try to distribute line items now. Orders, right, is also referenced. So let's try to also distribute orders. So we have a situation here, right? It's not possible to distribute any of the tables in an order that satisfies those constraints, right? So this is a special case. Everything is relation. There is a relation between all the tables. So what we actually have to do here before we actually distribute the tables is to drop those constraints that we just created. Yeah, that's it. So let's first drop orders, order store ID foreign key. Let's do the same for products. And let's do the same for line items, okay? Line items has 3 constraints that need to be deleted, okay? So once we delete those references, then we're free to go, okay? Now we can distribute the tables. Right now I'm executing the concurrently method. Of course, it won't make any difference because we don't have data here. But it will take some time, but it worked. So it returned successfully. And before we distribute the rest of the tables, let's take a look at that Citus tables view.
Right.
Let me just minimize a bit here. So as you can see, we have the table stores. It is a distributed table. The table type here could be also reference and could be also local, okay? The reason we're not seeing local tables here is because Citus doesn't automatically see local tables and manages them, okay? So there is another function you could add for Citus to manage those tables, and the reason is for a more advanced use of Citus. So we don't actually need to do that right now. The table size here, we have a few kilobytes of data. And the shard count is also a very important concept here. By default, Citus will create 32 shards for each distributed table, but that's configurable, okay? You can change that. You could, for example, have 48 shards. You could have 8 shards, okay? Ideally, it is a multiple of the number of cores you have in your worker nodes, okay? But since I didn't change anything here, it's just 32, okay? But keep that in mind, that's also a possibility. Okay, moving forward. Let's now distribute table orders. Now let's distribute table products. Let's do it in a different way. Okay. And also the line items table. Okay, having done that, let's go back to the Citus tables view. And as you can see, all the 4 tables are now distributed, okay? And the shard count is 32. And a shard in Citus is actually a Postgres table, okay? So what we have here is 64, 128 different tables distributed across the 2 worker nodes that I have in the cluster, okay? I also showed you the Citus shards view, right? Oh, this is very big. I hope you can see this well.
Yeah.
So yeah, for each table, like I said, there are 32 shards. Each shard will have an ID, okay? So here we're seeing shard 102, 350. It is located on worker 1, okay? And this one is located on worker 0. This one is located on the coordinator, and this is something that I actually forgot to mention to you guys. You can enable the coordinator to be an actual worker as well. So tables would be actually distributed to the coordinator table, the coordinator node alongside with the other 2 worker nodes. But there's a way for you to disable that and make the shards only be contained in the worker nodes. But we haven't done that. The shard name is actually the table name. So in worker node, if you connect to Postgres in this URL here, and you try to see the tables, you will find a table named like this. So Citus adds the shard ID as the suffix of the table that was created, okay? Just gonna go fast here. So line items and then orders. So with this view, you can see every shard in the cluster and where it is located, okay? Okay, moving forward. The next step, now that we have distributed the tables, is to actually recreate the foreign keys, okay? So what I did here is I added the store ID foreign key to the orders table. And this is, I mean, this is one of the beautiful things about Citus, right? So we're distributing tables and we're still having the power to create foreign keys. Let's do the same for line items. I'm gonna go faster here and create all at once. And then let's do the same for products. Okay. So now we have all the tables distributed in the cluster. And we also have the same foreign keys that we had previously. So we didn't lose anything after distributing the tables, okay? I think that's it. Are there any questions so far?
No questions. I think it's going on. I think Stephen is kind of answering that on the other chat. Yeah.
That's awesome.
Yeah. So thanks, Lucas. So wonderful to see, right? I mean, how to kind of set the order of distribution and how we drop and recreate the foreign key constraint after doing the distribution. So. So you can go ahead and summarize, Lucas, here, right, what you have shown.
No, yeah, we scaled the database. I didn't do it now because it would take some time, right, for the cluster to be resized. So we already had 2 worker nodes before the actual demo. Citus stat statement is something for the next part of the presentation, but it's already enabled, okay? Unfortunately, we had to skip the query execution benchmarks, but if you follow the link that we sent previously, there we will see how the benchmark was done, and it's very interesting actually to see how the performance improves after you actually distribute the data. Okay, but yeah, that's it. I think we can move forward.
Yep.
To the next part of the presentation.
Right. Yeah. So good news. We have distributed the tables right across all the worker nodes which we configured. We have taken care of the primary key foreign key constraint. We recreated those keys in the table. We have identified the distribution column, and using that we have distributed it. So now our environment is ready and to be used by the application as a kind of a multi-tenant database and multi-tenant and distributed database. Now it has gone into production. Now, another very important thing is how do we continuously monitor, because things change, right? I mean, the things change, the data change, because the business changes, right? So you have to continuously monitor and see that whatever design or the distribution you have chosen is working perfectly with the application. So we are going to covering that monitoring of the tenants in the multi-tenant database as part of this section. So if you see into like some of the key things which we're going to look into is which of the shard is really active or very noisy, so to say, in terms of the PostgreSQL terminology, right? I mean, when we say noisy, I mean, which shards are most being queried on. We also look into the data volume, how the data volume is, right? I mean, are there any skewness across the node? Is it like one of the node has like a lot of data, the other node is relatively idle and having less amount of data in there? And also how the queries are, like how many distinct queries are being kind of being submitted on the database. Now there are certain system tables which are present in there, which we can use and query and extract those information out. So as you can see on the text here, right? I mean, there are different tables, right, which we can kind of leverage. So if you follow, let's go on to the next slide. Right here. So as you can see here, this kind of gives, right. So tenant ID. So the tenant ID is nothing but the distribution column ID, which we have chosen. So in our case, the store ID is what is being represented here. So store ID 5, 336, 147, and so on. How many unique queries have been submitted on that? How many total queries have been submitted on that? What's the total time, the query time getting executed on these particular tenant IDs? So from here, if you look into the data, you see that tenant ID 5 is the most noisy because it's a lot of queries are kind of getting submitted here, and a lot of query time, a lot of resources are is kind of being consumed by tenant ID 5. So which kind of gives us an indication that because of this tenant ID, any queries on any other tenant ID which is there in the shard and on the node, on the same worker node, that will get impacted. So because this tenant ID 5 is really noisy. So as a step, what we should do is we should look into isolating this particular tenant ID. So if you go to the next slide, right? Yeah, so there we have identified in terms of queries, in terms of the compute being used, tenant ID 5 is kind of the most noisy. Here we are running the query on some of the tables and using some of the inbuilt functions. We are getting what is the storage space being used, right, by each of the worker nodes. And if there is any kind of a skewness in there. So so there are built-in CTS functions which we can kind of leverage in order to kind of determine that. So in the next slide, if we see, we are also looking into, we are also monitoring, okay, how many queries are going against single shard and how many queries are going against cross shard. There can be a situation, although you have done the distribution and you have ensured that there's a co-location, still there can be a situation where you are querying on multiple tenant IDs, and those multiple tenant IDs might be residing on different worker nodes. So you're doing cross-shard query in there. So we noticed here that majority of them, like roughly around 93%, is going on a single shard, so which is good. But there are like around 7% of the queries which are going cross-shard as well. So those queries, if they go cross-shard, right, cross-shard and cross worker nodes, those may have impact on the performance, and it might be that the queries are taking longer time to execute. Right, and then the previous prior slide we have seen, we can query on the size, right, and look into the different nodes, right, and see, okay, what's their size. So as you can see here, right, on the table node, on each of the nodes, there are certain nodes, like for example, the node 1 for the stores, right? Or in fact, over here it's the dash which is the coordinator node, is really small in size. Worker node 0 is again like it's not that big. But there are certain nodes which are kind of very have a bigger size, which means there is a skewness. From this report, we can very well figure out that there is skewness happening in our distribution, where one of the nodes has a huge data size, the other node has kind of a smaller data size. So which means that we may again have to do some kind of a movement, or we have to kind of move some of the shards from one node from the node which is kind of a big
Yeah.
size to a node where it's kind of a less size, or maybe create another node and then move it there.
Yeah.
You wanted to add, Lucas, here?
Yeah, I just want to add, Citus offers some functions to rebalance shards. Okay, so there are some strategies that you can use, and two most famous examples are by shard count, which will rebalance the cluster for so that the workers will contain almost the same number of shards in each, right? But like you said, for some reason, maybe some shards might contain much more data than the others, right? Maybe some tenants have more data than the others, etc. So what you can also do is to rebalance your shards by disk size, so that some nodes might contain more shards than the others, but the amount of disk used will be balanced, right? So that's something that you can do, and you can also write your own rebalance strategies. But that's again a more advanced use case of Citus. Okay.
Okay, yeah. So we are now going to look into like how we can isolate tenants in the multi-tenant SaaS. So as we have seen in the previous report, there are certain tenants which are really noisy. Noisy meaning these tenants are really resource hungry and consuming a lot of resources. That's impacting the performance of the query on other tenant IDs, right? So we need to isolate them because we need to give them more resource and dedicated resource out in there. So that's where we are going to be looking into, right? So we have to isolate the tenant's data to a new dedicated shard. So we have to pull it out from the shard where it's existing with other tenant IDs. So as you know, right, shard has like multiple tenant IDs in there. So we need to pull out in our example, tenant ID 5 from the existing shard and create a new shard, new dedicated shard, and move all the records for that particular tenant ID into that dedicated shard. And move the shard to the desired node in the cluster, either node which is less utilized, or maybe create a new node and just move the shard in there. The function over here, you want to go on that, like explain that function, Lucas, the isolate tenant to new shard?
Yeah, sure. So isolate tenant to new shard is the UDF, right? The function, the Postgres function that Citus offers for you to isolate a certain distribution key into a new shard, right? So like I said previously, shards in Citus are just regular Postgres tables that exist across the cluster, okay? So in a scenario where, let's say, store ID 5 is inside a shard in worker 1, for example, let's say this store ID is consuming a lot of resources from that worker, right? What we could do is we could isolate that store ID, all of store ID 5 data, into a new table. We call, again, shards, we call tables by shards here. And then after you do this isolation, after every store ID 5 is now on a different table, you can move that shard, in other words, table, to a different worker node, okay? So what this command is doing is just picking every row inside the shard that contains store ID 5 and then getting all those rows and migrating to a new table, right? So this is something you can do in order to prevent or fix some issues that some noisy tenants might be causing.
Right. Yeah. So as we were talking, right, I mean, new shard is created exclusively for order rows whose distribution column value equals 5. There is while you are doing this isolation, you have to keep in mind that it's not just the orders table having the tenant ID as 5 that needs to be moved to new shard. We also need to move other we need to move the other tables as well, where the tenant ID is equal to 5. So we do have a way where we can specify that, okay, not just isolate tenant ID 5 from orders, but also tenant ID 5 from other tables like the product table or the store table or the line item table onto another shard, so that the co-location which we have built in continues to be there within the shard and as well as on the node. So we have that way of kind of doing that. Lucas, you want to just show that function, how we can do that?
Yeah, I will actually show that during the exercise. I don't think
Okay.
we have it here on the slide deck.
Okay.
But
No
but there's a
worries.
there is a function that you can actually specify the shard ID you want to move from one node to another.
Right. Right. Yeah. Yeah. So you can move the tenants to the new shard to a dedicated node or the node of your choice using isolate tenant to new shard, and while using this function, you can specify the one of the parameters saying, okay, not just one table or all the associated table as well, and then you kind of get the which node, right? I mean, the node name where it's kind of getting distributed to, and the port of that node as well. Uh,
Yep, I
right.
think now I can actually
Show that.
demonstrate everything
Yeah.
that we've been talking for the previous minutes.
Sure. Yeah.
Okay, give me 1 second, please. Okay, so the first thing I want to show is what Citus stat statements is. Unfortunately, again, I'm gonna say again, we don't have data, but uh, when we query this table, we can have the query ID, which user executed this query, the database ID, what was the query, right? Executor, and here, most interesting part, the partition key, okay? The partition key is the distribution key, okay? So with this table here, we can actually see which query was executed for which tenant, okay? And how many calls happen for that particular tenant. And this is very useful data, right? Because we can also see what are the noisy tenants and what are the troublesome tenants, and how we can actually uh, fix that, right? There is also another table. I'm not sure actually if those are views or tables. I think they're views. This was not covered in the slide deck, but this is a new feature that was released in one of the previous versions of Citus, which is called Citus Stat Tenants, and it gives even more information about the tenants and how they're performing on your cluster. This one here, you can see we have the node ID, the tenant attribute, how many reads we have in a period, how many um, reads in the last period. I think the periods are like very predefined slices of time, right? That this query will give. We also have CPU usage, how many queries, and things like that. So this is very, very useful information that you can have in order to understand how your system is performing. Okay. I also want to show some of the queries that were highlighted on the slides, right? So this one is here, for example. We're getting the tenant unique queries, the total queries, total query time for each tenant. So this is very useful. This one was used in order to understand that tenant ID 5 in the slide deck was the troublesome tenant. We also have this order query here that you can see how much storage is being used by a specific shard, right? The percent of the table size and the store ID itself. So very useful to understand how each tenant is affecting the storage of your cluster. We also have this one here, which gives the percentage of cross-shard and sharded queries. So it's just a sum of calls and then just getting the percentage of this, right? So very, very useful query as well. And lastly, I want to show you something that's very interesting. It is the rebalance table shards. I want to execute this because we don't have any data here, but this is what I told you guys about. So we have different strategies for the rebalance operation. So we have by disk size, we have by shard count, and you can also define your own strategies using Postgres functions, okay? So this is very, very useful things, right? So this is all about monitoring. I want to show you now how the isolate tenant works. So we can actually execute this without having any data, because what will happen in the backend is that a new table will be created for this new shard that will be created for tenant ID 5. So as you can see, there is a new shard in the system right now. So let's see where it is stored right now.
Yeah, and Lucas, I want to highlight that Cascade is the one which you specify ensures that all the related shards, related tenant records are also kind of copied to the new
You're
shard.
right. I forgot to highlight that. Then thank you. Yeah. So Cascade is used for that, where shard ID equals. Okay. So okay, we have the new shard that was created after the isolation, and it is stored on worker 1. Okay. Let me actually do something here. I need to fill. We're gonna move this shard to worker 2, and I'm gonna show you guys how to do that. 1 second. This is the shard ID. The function that will execute is Citus move shard placement. And what we have to do is first specify which shard we're trying to move from where to where. So here we're moving from worker 1, and then we're going to move it to worker 2, okay? It's saying non-existing node for some reason. Let me just, maybe the URL is wrong. Oh, it's worker 0. Yeah, we don't have worker 2.
Yeah, 0 and 1. Those are the two.
Yeah, it's 0 and 1.
Yeah.
Okay, so we're going to move from worker 1 to worker 0. Now it should work. Okay. So if we execute that same query, filtering by the same shard ID, it should be showing worker 0. Okay. So yeah, so it worked. So what we did here is we moved everything from that table on worker 1 to a new table on worker 0. It was very fast because there is no data, right? It would take a bit more time to do that if there was data. Okay, so I think that's it for the tenant isolation and move shard placement. If there are no questions, I think we can move to the last part of the presentation.
No, yeah, I don't see any questions here. Maybe on the other chat, Steven is kind of answering those questions. So we're good here right now. Yeah.
So one thing I want to highlight is we could have added a new worker node. I didn't do that, okay? But we could have, and we could have moved that same shard that we moved to worker 0 to that new worker. So this is very powerful because one thing you can do with Citus and Cosmos DB for Postgres is you can isolate tenants into their own nodes. So if there are customer requirements, let's say that their data shouldn't be stored in the same place as other customers, you could isolate all of their data into their dedicated node. Okay, so this is a possible scenario for Citus. So it's not only about performance, it could also be about some security guarantees, let's say, for example. So moving forward, now we have a knowledge check for you guys. So here's the first question. So yeah, so you can vote at the link that's on the screen right now. So the question is, when preparing multi-tenant tables for migration from a single node to a multi-node cluster, what classification is applied to tables that can be logically distributed by the chosen distribution column, but don't contain a column directly referencing it? So we're going to give you guys 2 minutes to answer this question, and then we'll move forward.
Right, yeah. Just to give a hint, we covered in detail a particular table where we introduce the distribution column. So should be easy. In 1 more minute. Okay.
Yeah.
So hopefully, yeah. So I think we have 2 minutes. So
Yeah. So
hopefully
the
people.
right answer is needs backfill. So like we said previously, some tables might not have the distribution column, so you have to add them and then backfill them with the distribution data, right? You want to add something here, Rajnish, or can we move forward to the next question?
No, I think we can move forward. I think we have discussed backfill in detail before.
Yeah. So next is, which distribution function is the safest to use for write-intensive tables when migrating a production multi-tenant database from single to multi-node? Again, 2 minutes.
Right. Yeah. Again, this is we discussed because it's a write intensive table. So obviously, any locking to the table will mean that the application is there'll be an application outage, right? So we have to use a function which allows you to write on the table as well as get it distributed across the shard or get it distributed across the nodes. So another minute or so, and then we'll answer that. So we had two functions, right, which we discussed in detail: create distributed table and create distributed table concurrently. So one of these, just to kind of give you a hint, should be the answer.
Yeah. Okay, I think we can
Okay.
move.
Yeah.
Yeah. The right answer is create distributed table concurrently.
Right. Yeah.
All right, moving to the next. So when monitoring activity in a multi-tenant SaaS database, the ability to view database usage and statistics on a per-tenant basis is crucial, right? What built-in view allows you to get clear insights into what tenants are doing, what your tenants are doing?
Yeah. This we covered as part of the monitoring of the distributed cluster, and we talked about some of the existing views and tables. Okay, yeah, I think we are good. We can answer that, Lucas. That's okay.
Yeah,
Yeah.
Citus stat statements is the right answer. That was the first query that I executed in the exercise. All right, so going forward, let's do a quick summary of what we talked today. When you want to move from single node to multi-node in Cosmos DB for PostgreSQL, you need to prepare your tables, right? You need to change your primary keys. You need to add the distribution key for the tables that do not contain it. Backfilling is crucial. You need to fill those that new column with the distribution key, right? So when you prepare and you have everything ready for distribution, then you can add your new nodes and then distribute the tables with the right method for your situation. We have two of them, right? We have the create distributed table, which will block writes, and we also have the concurrently version of it that will not block the writes. Okay, so it's very important for you to understand what are the different options you have. And once you've done that, there are various ways that you can monitor your application and how your tenants are performing. A lot of queries, a lot of views that Citus offers. And one very cool thing here you could do, for example, is since Citus is just an extension for Postgres, right? You can use I don't know, some observability tools such as Grafana, for example, to connect your database and then show the statistics for each of the tenants there in a very easy way. Okay, after this, clean up your resources if you try to follow this on your own. So there's a guide, there's a link that we're going to show you after this slide that you can follow the same things that we did here and do it on your own. So those links are here. They're resources. Please check them. It's very interesting. Of course, there are any questions, you're free to reach out to me. Let's see. Yeah, there is an interactive learning exercise that I said, some videos, and it's very important for you to practice on your own because the concept might be easy, but it's always good to do that. This is, just to reiterate, this is the part of a whole series that was made for Azure Cosmos DB for Postgres. This is not the first lesson. I'm not sure if it is the last though, but I know there are a bunch of others, and this is very interesting material. And yeah, please go check them. And yeah,
Right.
yo, this is the last. I just heard that.
Okay. Yeah. So just to kind of how you can access Azure Cosmos DB for PostgreSQL, just go to Azure portal if you have access to it, and just search for Azure Cosmos DB, and within that you'll see one of the options as PostgreSQL, and just click and start kind of follow the guide and start deploying it in there. So once it is in there, just follow the guide and then you're good to go.
Cool. Yeah, I think that's it. Thank you guys very much for your time. I hope you enjoyed this series. And yeah, thank you.
Yeah. Thanks a lot. Thanks for your participation. Thanks, Lucas.
Thanks, Rajneesh.
Thank you.